Yep, great. Okay. Thanks for the opportunity to talk at this symposium. Sorry, I ended up fleeing back to Brisbane last night. What I want to talk to you today about is some work that we pretty much wound up a little bit about 2 years ago around AI in COTS monitoring surveillance, but we've been moving on in a bit of a new direction that might actually be able to circle back into this space. So firstly, I'd like to acknowledge the traditional owners of land and sea countries where we've conducted our work. I would also like to, I'm presenting on behalf of some contributors from QUT, Faraz, Serena, Melissa and Ricky. But also I need to thank, in this particular work, AI requires lots of data, and I've been able to get a lot of that data through the assistance of the COTS control team, particularly those on HERO back in 2015-16, Queensland Museum and AIMS. So I'm an environmental roboticist, and what I'm particularly interested in is creating tools that can operate in very complex environments by themselves and collect scientifically relevant data and samples. So you'll see here sort of two generations of robotic systems. The one on the left is the COTS bot, which we designed to do robotic culling of starfish. And it is actually a very capable vehicle, but as Morgan sort of gave a bit of a spoiler alert in his first talk, there's issues around what is visible during the day, particularly from a topward looking vessel. But there is some opportunities to exploit this type of technology a bit further. So this is actually work that started around 2005 when I was at CSIRO, and at the time there was still some talk around, well, a lot of talk around crown of thorns starfish, and we thought it would actually be really cool to make a robotic system to do COTS control. And this is well before AI was mainstream. Even though AI was around, it sort of hadn't hit the thing. And we were lucky enough to get some data from Hugh Swetman and Kate Osborne from AIMS, and we ran what was considered pretty state of the art back then in local binary patterns. And we were super wrapped with this, work that, we were getting 65% detection accuracy, taking 2 minutes per image. That was state of the art. But what it also meant was, as a robotic solution, we couldn't do real-time surveillance. We couldn't do real-time detections or control. So we sort of we still worked on these robotic systems, but nothing really to do with crown of thorns. And it wasn't really for us until about 2015, there was 3 key enablers that made us revisit this. This is when I started at QUT, actually. The first one was bile salts. Prior to that, with the multiple injection solutions you needed, it was impossible for a robotic system. It was hard for a human, but impossible for a robotic system. Through AlexNet and a few other sort of AI learning techniques, deep convolutional neural networks came out, which we just tend to call machine learning AI now. And we had an explosion through the computer gaming industry, some very small low power graphic processor units. But what we wanted to do is exploit these types of technologies because we saw there was opportunities. One was to create a very high performance COTS detector using machine learning. Build around that some robotic systems to do that detection and the control. But also the way that we work at QUT is we primarily focus around robotic vision and stereo vision. So there's lots of other information we start to get when we use stereo vision and other techniques like size distribution, substrate, percent cover. We can work on 3D geometry, rugosity, all sorts of things. And we record like depth and other environmental data. But what I'm going to focus on is sort of the key learnings we got out of this explosion in deep convolutional neural networks and the ability to process this information in the field. Now, with any AI machine learning type approach, you need data and lots of it. And if you ever go, like if you say, I want to, as an ecologist, you go to a roboticist or a computer scientist, say, I want to do a machine learning system. I say, oh, where's the labeled data? That is the holy grail of what we want. We want labeled data to train our networks. So, and that's why you'll see a lot of people tend to do what we call transfer learning, where we actually have networks that are trained not on anything to do with marine typically, but you actually get a very robust set of weights to start off with, and then you use your data to train typically the top few layers of the network to really customize it towards your application. So there's pros and cons of doing that, and you might get some unexpected behaviors, but that's typically how a lot of people work unless you have lots of data. So for us, when we started this program back in, well, the new second phase of the program in 2015, was we actually just trawled the internet for what we had, and use YouTube and GoPro and sort of just imagery from Google. These help start this is in the process while we're trying to get new types of data. This actually helped well to get started, but the problem is these are all glamour shots. They're perfectly framed, perfect lighting. They're not realistic of what you'd get in the real environment. So then we went to some other novel ways of generating data, and here's just some examples. Through the Queensland Museum, we're actually able to borrow some preserved samples through our biomedical team. We actually took them to the hospital and did MRIs on them, and we actually able to 3D print crown of thorns to help with some of our training. We're trying to do some synthetic data generation at the time. We're using different images, different ways of collecting the data, because obviously in the field you have visibility constraints, you have motion blur constraints, and we're trying to simulate all those. One of our most prevalent forms of data, and this is when we started to really work with the guys from Hero, the COTS control team, we actually made essentially selfie sticks. We put GoPros on the applicator guns, devices, to collect data for us. And this turned out to be an incredible amount of data and quality data that we required. And you can see here in the image, this is actually probably getting towards late 2015. So you can see the main image is actually from the selfie stick. You can see the end of the applicator there. The diver there is just towing around the robot at that stage, because we're also trying to collect data around the difference in cameras and the performance variation that you get from those. So this sort of relates in some way to the data that Morgan presented at the start of today. From our perspective, we're interested in generating a system that could do COTS control as well as COTS detection. And we ended up classifying a heap of data that we had into 4 subcategories, which we called easy, which the COTS was pretty much visible. Medium, which was about 30 to 40% of the COTS was visually available to do the injection. Hard, which we could still detect, but from a robotic perspective, we had risk of damaging coral or the equipment or getting stuck, which we didn't want to do. And impossible, which from a video sequence was this even tricky for a human to detect. And this is just some example results from that. So this is just from an 11-hour sample of one of the GoPro selfie sticks that we made. And I think there's probably about 250 animals in that data set. You can see sort of corroborating some of the early results that, of those probably easy ones, which most people would see as you've been pulled over in a manta tow, probably only about 25% of the visible ones. For us, we were only focusing for our study on the easy to medium data. But in the end, I think we have a very comprehensive data set. So we pretty much got rid of all the original internet trawled stuff and focused on this data plus data that we collected with our vessels themselves, our robotic vessels. And in the end, we end up with we've currently got about 105,000 images in our database that make up the COTS detector. Now, I should stress that this is a COTS detector, not scars. And I appreciate that for manta tows, probably the precursor is more of a scar observation, and then you'd focus down on the COTS themselves. So one thing that we had to do was obviously generate quite a robust COTS detection system. We did not want to be, for our case, injecting anything that wasn't a COTS. So we just need to be absolutely certain that what we were observing was a COTS. So we worked on the false detection rate. Here's a couple of sets of data with about nearly 3,000 images in each. And this is the amount of false positives. So the ones that we would define as being a COTS, even though there was no COTS there. This is without tracking, I should say. So from the data, that black line is about 0.5% error. And we'll get to what we actually end up choosing in a second. But what we found also was, because we actually have a robotic system and we have very accurate sensing, probably down to about 1 millimeter of altitude above each pixel, we can actually then try and work out when we actually got the best types of data. And what we found for our particular system was that with altitudes above the seabed, from about 0.6 to about 2.2, 2.3 meters, we had our best precision. That is the best number of true positives to false positives. And this is just a subsample of one of the data sets that we have. So that actually was great for us because as a robotic system, then we can control very accurately our position in the water column to ensure that we're in that sweet spot to make sure that we have some good data. And we can do multiple COTS detection. So what we ended up with is once we end up choosing our threshold, so we actually said our inference threshold per frame is 80%, and that's without the tracking, which increases it even more. We get 99% detection accuracy of those ones that are visible. And the other cool thing was we had to optimize the algorithms based on 2015 technology. We could actually get to about 10 hertz processing. So that's actually done on the robot. So as we resurface, we actually already have an estimate of the numbers of animals that we saw along that transect at different degrees of influence. As Brett just mentioned, observing imagery and trying to find COTS is very hard because they're only in the scene for very short periods of time. So that is one of the benefits of using these types of systems, because you have multiple frames going over. So if you had to watch this footage for quite a bit of time, you would be probably seasick if you're on land. But what you see, there's some circles. We actually do inter-frame tracking to allow the robot to station over it. So from that, we've developed essentially a great COTS detection system and a robotic system around it. One of the challenges obviously was the number of starfish that were available during the day, particularly if you're in outbreak areas, it's a more viable option. When they're really sparse and very cryptic, obviously you wouldn't see them. And because we weren't looking for scars in this implementation of the detector, it wouldn't capture those. So we're only looking for pure animals at the time. But from that, we've actually developed some new tools that we can run different AI models depending on different tasks that we're doing. So this is the Ranger bot that sort of evolved through the Great Barrier Reef Foundation and Google. We can attach to different attachments, different payloads, whether injection systems or whatever. But what I wanted to show, sorry, I'm trying to run that movie again. And for anybody that's actually interested, this is something I've been wanting to do for a while, is to do nocturnal surveys. This is some stuff I've been doing in the Philippines, not related to COTS, but we can find we can do some really good stuff at night, and I'll be very interested to apply this in the COTS scene. But the whole focus now around our technology development is portability. You can see that the items on the right can either be inflatable, back down into a backpack to take anywhere in the world, essentially, and we can train different models and different things like that. The other key aspect is on usability. I'm not typically there for a lot of it, so we've put a lot of effort into the usability and interfaces of these types of technologies. So going on from just a comment that Brett just made in his presentation was, okay, how effective are these types of technologies when you compare them to humans? And And this is just some example data. The bottom graph, the top graph shows essentially your field of vision, and you have very good spatial resolution immediately in front of you, but your periphery through the cone shells are really great at picking up motion cues, and then you direct your visual attention to that. And that's one reason why humans can be better than robotic systems, because your attention, due to potentially a scar coming past, which is a motion cue in your periphery, you would then focus on that, where a robotic system might be blinkered due to its field of view, being a bit narrower, to pick up those motion cues. However, in saying that, there are options that we can really start to exploit when you use different types of cameras. You can go wide angle lenses, but you can distort get distortion of the periphery, which means that your spatial resolution becomes a lot less. The higher resolution, higher altitudes, you can go very high resolution cameras, and this is something that I know a couple of the colleagues at AIMS are looking at, and we can use camera arrays.
Matt, you don't have much time left. Could you wrap it up in the next couple of minutes, please?
Absolutely, absolutely. So very quickly, you can actually use neural networks to actually improve the image visibility, and this is something we do using generative adversarial networks. Other areas, we're now looking at these tow bodies as well for different vehicles. We actually have these in the Philippines right now for some coral spawning work, where they get towed behind. We can have multiple vehicles towing these to collect data. One of the cool things is that we can go over very shallow areas, so we can go over reef crests and things like that. And just give you a quick view. This is actually at Heron Island in 40-knot winds, where actually they cancelled the ferry. So anybody's been there when they cancelled the ferry, you know, it's pretty rough. But we were still able to operate, which is great. Something that Serena's working on is a new type of machine learning technique where we have what we call few-shot learning, so you need less data. And here, in this particular example, is when you see a tick, is where the robotic system's allowed to deploy coral larvae. This is a new application that we have. These models are very generalizable. We actually trained it on Lizard Island data, and we've been applying it at Heron and one in the Philippines. And when you got across it, it assumes that the substrate isn't suitable, so we do whole of image sort of estimates of where we are. So just in summary, AI is transforming the way that we can classify natural scenes to varying degrees of certainty or uncertainty. And I'll put the thing up there is if you don't use them correctly, you can get them wrong. We've been able to develop some novel data collection methods. We're now focusing more on, through some field management teams, on detecting scars as well as COTS. And we see that these types of portable AI-enabled tools are really sort of being able to scale monitoring and intervention tasks, not just for COTS, but a whole range of other techniques. So if there is interest in these types of tools, please just reach out. We're happy to let you have a go at them and go from there. So thank you for your time, and